Okay, now part 5 of our revisit to space-time diagrams. We've tried to clean up our diagram from last time just a little bit. So let's review what we've got here. We've got Alice's plot, her frame of reference, the XA axis, the T sub A axis in normal right angle configuration. And over the last couple of video clips, we've shown that we can put Bob's frame of reference on the same plot if we draw the X sub B axis at an angle like this and the T sub B axis at an angle like that. And of course, we figured out what the angles have to be. Remember, the T sub B axis in particular is Bob's world line. He's sitting in his rocket ship, traveling velocity v. Alice is observing from his perspective. He's just sitting at X sub B equals 0, which is the T sub B axis here. To do the exact transformations, of course, we can use our transformation equations here, but the plot gives us some insights just diagrammatically or pictorially of things like time dilation and length contraction. We tried to point that out a little bit last time. And this time we want to point out that relativity of simultaneity is very evident from the plot as well. But again, let's orient ourselves so that, note for Alice's plot, we have lines of simultaneity. T sub A equals 1 is this line. We'll get to the red dots here in a second. T sub A equals 1, T sub A equals 2, T sub A equals 3, and so on and so forth. We did not draw lines of same location for Alice just because it gets to be a little much on here, but they would be, X sub A equals 1, X sub A equals 2, X sub A equals 3, and so on and so forth like that. Now, what about Bob's plot? We have the T sub B axis at an angle here, and the X sub B axis at an angle this way. And note, in particular, we've got lines of simultaneity for Bob on here. Those are the lines that, just like Alice's lines of simultaneity, are parallel to her X sub A axis, because this is really T sub A equals 0 here. Bob's lines of simultaneity are parallel to his X sub B axis. And so the X sub B axis is essentially T sub B equals 0. The time he measures is 0. Then we've got the T sub B equals 1 line, 1 light year if we're using light years, and C is light years per year, 1 light year per year here. T sub B equals 1 is this line. T sub B equals 2 is this line. T sub B equals 3 is this line. And as much as possible in our diagram, remember, we've actually figured out exactly what the spacing is between those lines of simultaneity for the T sub B's, and similarly for the lines of same location, X sub B equals 1, X sub B equals 2, X sub B equals 3. Now, in certain places my diagram's slightly off there, but hopefully you can see what's going on with that. So, now let's get to the point here, is that let's say that these red dots are flashes of light. Let's do Alice's perspective. Flashes of light. We're actually going to look at the T sub A equal 2 line of simultaneity. So if all I told you were these were flashes of light, maybe flash photographs that Alice is taking in her frame of reference, note, as far as she's concerned, they're all simultaneous. They all occur at T sub A equals 2 years if we're doing light years per year for C, or 2 seconds if we're doing light seconds per second. So they all occur at T sub A equals 2. Again, we know that Alice has her line of synchronized clocks. Bob has his line or lattice of synchronized clocks as well. So in Alice's frame of reference, she shoots off flash photographs on her line of synchronized clocks at T sub A equals 2. And those are specific, unique space-time events at each of those locations. And in her frame of reference, they all occur at T sub A equals 2, and I've drawn them so they occur at like X sub A equals 0, X sub A equals 1, 2, 3, 4. So we'll assume she just has clocks at those locations, and they're synchronized for her. Let's see what the diagram shows us in terms of Bob's perspective on this line of flash photographs that have gone off. Well, let's start with this one right here. And actually, before we get into that, let's situate ourselves. Remember, Bob is moving to the right, positive X direction. From Alice's perspective, from his perspective, he sees Alice going in the other direction. Okay, so if these were clocks in Alice's frame of reference, she's taking flash photographs of, Bob, from his cockpit, would see them going this way. They're going to the left. In Alice's frame of reference, they're stationary. They're -1, 0, 1. The lines of same location. They're not moving. In Bob's frame of reference, they're moving to the left. Okay, so let's start with this clock right here, that flash photograph of Alice. And we can see that it's on the x sub b axis. Okay, so that's t sub b equals 0. So to Bob, that flash would occur at t sub b equals 0. The next flash here is on a different line of simultaneity for Bob. It's at about 1/2 maybe. T sub b, so you have to imagine these lines of simultaneity for Bob parallel to the x sub b axis. So this is another time line, as it were, and that's maybe at t sub b equals 1/2 there. Okay, and then this third flash here occurs maybe just past t sub b equals 1 there. Fourth flash occurs at maybe about 1.7, 1.8 to Bob, and this flash just past TB, the TB equals 2 line of simultaneity, and then this flash here maybe, I don't know, about 2.7, something like that, just under TB equals 3. So to reiterate, what we're saying here is that Bob observes this flash to occur at TB equals 0, this one maybe about 1/2 second or year, depending on the units we're using. This at about 1, maybe about 1.7, 2.1, 2.7, something like that. Okay? If we wanted to get exact numbers out of this, remember we could use the Lorentz transformation equations. In other words, Alice says, okay, I've got flashes of light at t sub a equals 2, and x equals 1, 2, 3, 4, and 5, and 6, or whatever. We could take those values, plug in Alice's xa and t sub a values for each of those flashes, and get the xb and tb values that Bob sees. Okay? But the diagram shows us more pictorially what's going on. But if we wanted the exact values, we could get them from the equations. In fact, of course, we built this using the Lorentz transformation equations. So what's the conclusion here? The conclusion is clearly we have relativity of simultaneity. That clocks that are synchronized in one frame of reference, Alice's frame of reference, are not synchronized in Bob's frame of reference. In other words, he sees this clock go flash first, and then this clock, and this clock, this clock, this clock, and this clock, in that order. Okay? Now to Alice, remember, all those clocks are synchronized. So when the flashes go off, she will see the same time. The flash photograph will show the same time on each of those. But Bob sees the flashes occur at different times, not the same time. So let's just say, well, let's not just say, it is right here. All the times shown on those flash photographs are t sub a equals 2. 2 years, okay, on those clocks. Bob will say, okay, on the first clock, that one happened at t sub b equals 0. 0 years. This one happened about 1/2 year. This at about 1.1, 1.8, and so on and so forth. And note another thing about this. So first of all, relativity of simultaneity. Bob is saying, Alice, your clocks are all messed up. You may think they're synchronized, but clearly I see them as unsynchronized. These flashes are occurring at different times, and even though the times in the photograph show that your clocks are reading the same time when the flashes occur, the flashes are clearly not occurring at the same time, which means your clocks are not synchronized. In other words, what Bob is saying really is, in my frame of reference, your clocks are not synchronized. Where Alice is saying, well, clearly they're synchronized, but that's in her frame of reference. The other thing we can get out of this, qualitatively, is leading clocks lag. Because think about this a minute. Here's this line of clocks, and Bob is seeing them flash one after the other. This one, then this one, then this one, then this one, slowly, of course. And again, these clocks are heading leftward compared to Bob. And since we know when they flash, they all read the same time. So when this one flashes, it reads 2. When 2 years, 2 years, 2 years, 2 years, 2 years, 2 years. So to Bob, this one flashes first and it reads 2 years. This one flashes last and it reads 2 years. What is the leading clock from Bob's perspective? This is the leading clock here. It's moving in this direction. So as he's observing Alice's clocks go by, this series of clocks, this is the leading clock. It flashes last and reads 2 years. This one flashes first and reads 2 years. this clock is definitely behind that clock by a given amount that we could actually figure out from the diagram or the Lorentz transformation equations, or simply by our dv over c squared equation we got when we did a quantitative analysis of leading clock's lag. But again, space-time diagram like this now where we can put both frames of reference on the same plot allow us to analyze things without necessarily going into the details of the equations because, again, this is built on the equations. And we see here that, yes, we see relativity of simultaneity and we see leading clock's lag. So this is one of those things. Ponder a little bit. It's useful even to construct your own. Get out some graph paper if you have some and work through essentially the exercise we did the last couple of video clips to construct this. And then just sort of plot various things on there. See if you can figure out what's going on from Alice's perspective versus Bob's perspective.